By the end of the 19th century, classical physicists universally treated light as a continuous, sweeping electromagnetic wave. In 1887, Heinrich Hertz discovered an anomaly that challenged this consensus during his experiments with electromagnetic waves. Hertz found that when ultraviolet light struck a metal plate, electrical sparks jumped across a gap more easily. The light was knocking electrons, negatively charged subatomic particles, out of the metal surface. This phenomenon was named the photoelectric effect. This spark of ejected electrons presented a physical contradiction that classical laws of physics could not explain. Wave theory predicts that energy is distributed continuously. This means a dim light should take hours to transfer enough energy for a single electron to escape the metal. Experimental reality showed the opposite. Electrons are emitted in less than a billionth of a second, regardless of how dim the light is. There was also the threshold frequency. Scientists found that low-frequency red light, no matter how intense, cannot free a single electron from the surface. Yet high-frequency ultraviolet light knocks electrons free immediately, even if the beam is incredibly faint. Because light was expected to wash over the surface like a wave, these observations showed that the classical model of energy absorption was broken. In 1905, Albert Einstein proposed a solution that abandoned the concept of continuous waves. He suggested instead that light travels as a stream of discrete, localized energy packets called quanta, or photons. This is Einstein's photoelectric equation. The term h nu represents the energy of an incoming photon, where h is Planck's constant, a value used to calculate the energy of light based on its frequency. Einstein described this as a one-to-one interaction. A single photon strikes a single electron, transferring its energy in a sudden impact. This solved the time delay problem. Because the energy transfer is a single collision between particles, it happens immediately rather than building up over time. This leads to the next variable in the equation, the work function, or phi-0. The work function is the minimum energy barrier an electron must overcome to escape the attractive forces of the metal. If the incoming photon's frequency is too low, it lacks the energy to meet this minimum requirement. The electron stays trapped, explaining why red light has no effect. If the photon energy exceeds the work function, the electron breaks free. Any leftover energy becomes the electron's kinetic energy, which determines its speed. Increasing the intensity of the light simply sends more photons, which releases a higher number of electrons. However, it does not increase the speed of the individual electrons being released. While Einstein's mathematics matched the experimental data, his photon theory was highly controversial and required physical proof. American physicist Robert Millikan was a skeptic who spent 10 years attempting to disprove Einstein's photon hypothesis. Millikan used a retarding electrical voltage, called a stopping potential, to repel and halt the fastest electrons emitted from the metal. This equation relates stopping potential to light frequency. Einstein's math predicted that these two values would share a linear relationship. Millikan painstakingly measured data across different frequencies for several metals, plotting the results to see if they would deviate from Einstein's prediction. If the data points curved, the photon theory would be proved wrong. Instead, the data points formed a straight line. The slope of this line matched Planck's constant divided by the electron charge, providing exact confirmation of Einstein's equation. Millikan's attempt to disprove the photon hypothesis resulted in its definitive experimental proof. Both Einstein and Millikan were eventually awarded Nobel Prizes in physics for these discoveries. This proven equation showed that light acts as a discrete particle, ending the classical worldview and establishing the foundations of quantum mechanics.